Alright, next up we have three more quadric surfaces to talk about, and they are what I refer to as the ambiguous cases. The reason I call them the ambiguous cases, well, you'll see in just a moment. So first one. First one is a very precise form. The very precise form that it takes is z squared over c squared is equal to x squared over a squared plus y squared over b squared. If we take a look at the traces, this time instead of actually writing out the word trace, I'm just going to write out which trace I'm talking about. So for the xy trace, go ahead and cover up that z variable. Oh, casting shadows. That's no bueno, like we say in French, no bueno. We see an x squared plus y squared. That is indicative of an ellipse. The xz trace, even cast in shadows, will be okay. I see that we have squares on opposite sides of the equation, so if I were to bring this over to the other side, I would have a difference of squares. That is a hyperbola. Similarly, if I cover up the x variable, we have squares on opposite sides of the equation, and that is once again going to be a hyperbola. Now this, honestly, is probably something that you've seen before. I'm going to do my best to draw it. This is known as a fantastic mechanism for ice cream. This is known as a cone, or more specifically, the elliptic cone, because cross-sections are the ellipse. Now that means that if I were to cut it straight across, cross-sections would be ellipses. However, if I were to cut it straight up and down, I would have an associated hyperbola on the top side and on the bottom side. There are some fantastic visual representations that you can find in our book for how that works. Now, suppose that I were to take this and bring it over to the other side. I would have a 0 on this side. Suppose, however, that I bring it over to this side and I don't have a nice precise 0. Instead, I have literally any other number left over. What you're going to find is that all of the traces, in this case, are identical to the previous case. And I will leave it to the viewer to sort of cover up some variables and verify that you get the same thing. Now, for all intents and purposes, this means that we should be getting essentially the same thing as up here. Now, imagine for a moment that I take this cone, and instead of having just a point here, that it actually connects smoothly, and there's just a little bitty gap in the middle there. So hyperbola over here, elliptic cross-sections, and at no point in here do we ever stop having an elliptic cross-section. More details on that in just a moment. This is known as a hyperboloid. I mentioned in the last video that when you have two of the same kind of traces, that becomes a noun and we add oid at the end. Works here as well. Specifically, this is a hyperboloid of one sheet. We say it's of one sheet because there's only one solid thing going on here. Now, a hyperboloid can actually be created fairly simply by taking a nice object like this, put it at an angle, and then rotate about an axis, and it will sweep out a hyperboloid. I will toss in an appropriate image so that you guys can figure out what I'm talking about. Now, suppose also that rather than moving the z squared over to the other side, I instead move the x squared and the y squared over to the side with the other stuff. If you were to take a look at the traces, once again, x, y, they're on the same side. They have both negative coefficients, which means that we are going to see an ellipse. For the xz, once again, you're going to see the hyperbola. And for the yz, once again, you are going to be seeing the hyperbola. Exact same three traces as what we saw in the previous cases. Now, imagine taking a cone And instead of widening the gap between them, imagine cutting off that gap a little early and sort of molding it so that the two pieces don't touch each other anymore. So what you would get is something that looks probably a little bit like this on one side and a little bit like this on the other side. Those are supposed to be hyperbolas. I kind of made them look like parabolas. This is known as a hyperboloid. Same sort of naming mechanism as before. And this one is a hyperboloid of 2 sheets. They say it's of 2 sheets because, well, there's an upper side and there's a bottom side for the hyperbolic portion. So the big question becomes, how do I tell one of them from the other? And that is an important question to ask. What I'm going to encourage you to do is solve for the elliptic trace. That is to say, see if you can get the portion that looks like an ellipse by itself on one side. So in all 3 cases, this is the thing that I would be talking about. Now, we'll do a quick little side-by-side with the previous sheet. Now, the cone is already in that form, so we'll just go ahead and copy down z squared over c squared. In the second case, I would be adding this over to the other side, so this would be z squared over c squared plus 1. And in the last case, I would need to move it over to the other side and then multiply both sides by -1. So here are the important things to ask yourself about this case, or these cases, as it were. Can the thing on the right-hand side ever be negative, and can the thing on the right-hand side ever be 0? If it can be 0, then there is no split, there is no domain issue. In the third case, if I choose the value of z to be between -c and +c, this winds up being less than 1, then I subtract 1 from it. I cannot take a square plus a square and wind up with something negative. That means that on the z-axis, there's going to be a little gap in between +c and -c where this thing does not exist. Now that means that there's going to be a lower portion and an upper portion. Well, that right there, that's your 2-sheet hyperboloid, or hyperboloid of 2 sheets. Now, if it can become exactly 0, which is the case, the only way that we can get exactly 0 out of this is if this thing is squared, if this thing is 0, and if this thing is 0, and if this thing is 0. What that means is that everything comes together at one single point where all 3 of the things are equal to 0. In order to come to a single point, you need straight lines in order to do that. That's how we wind up with a cone out of this. In the third case, it is never possible to wind up with anything but an ellipse here. I mentioned on the previous page, I'm going to bring back the previous page real quick, that when it came to this, the cross-section is always an ellipse and it can never be anything but an ellipse. That's a hyperboloid of 1 sheet. Now, this is the way that I try to remember it. The way that my students in the past have told me to try to remember it is, cone is pretty easy to figure out because there will be no leftover +1. Outside of that, put it into this standard form and count the number of negative signs. If there's 1 negative sign, it's 1 sheet. If there are 2 negative signs, it's 2 sheets. If you like this better, well then you're probably a student as well. I'm not saying it's bad, I'm not saying it's good, I'm saying whatever it takes for you to remember it, I'm for it. Let's do some examples.